Good morning, everyone. My name is Baran Mazarov, and today I'll talk about how can we use MFM for doing design and optimization. My talk will be mainly about project optimization. However, I'll touch some of the features which are used in shape optimization. So why do we need optimization? Well, I'll start with this example, classical example of designing an airplane. And for a passenger, it's important for the airplane to transport themselves safely from point A to point B. Well, for the company, they want to make profit out of it, so they want to put as much weight as possible on the airplane. Therefore, they would like to reduce the weight of the structure and at the same time transport the passengers safely. And that's how it's gone back in the 90s. And that's the example of how project optimization can be applied in this process. So project optimization aims to distribute material in a design domain, which is given in orange here on the slide, in an optimal way by minimizing an objective function and fulfilling set of constraints. So that's an example of designing the rib of the wing of Airbus 380, and the goal is to minimize the weight and at the same time keep stiffness up to a certain level, so this will fulfill the requirements for safety. We start with the blank domain. So the distribution of material is described by a density function, which takes value 0 if the point is void, and value 1 if the point is occupied with a solid material. So we start with the gray domain, we compute our objective, we compute our constraints, we compute gradients of the objectives and the constraints, and we start updating our density distribution. And after 150 iterations, we'll end up with this relatively black and white design, which is going to the engineers, and then the engineers will start interpretation, and you can see the whole process of implementing this in the wing of the airplane. So mathematically, the formulation, the optimization formulation can be written in the form which is shown on the slide. So we have an objective function, which could be mass, could be compliance, could be anything which you can imagine you would like to compute and optimize for. Subject to a set of constraints. The first constraint represents the physics written in a residual form. Second constraint, we can add small physics, we can mix physics in the optimization process, so we can optimize for fluid mechanics, heat transfer, combined with requirements of solid mechanics behavior. We can work electromagnetics if we want, and so on. And we can have set of constraints, of course. So, for example, if we minimize for the mass, we would like to constrain the maximum displacements, or we would try to constrain the compliance of the system. If we solve for temperature, for example, we would like to constrain the maximum temperature in the domain or the maximum flux. And of course, what we optimize for is the density. Usually, this density is transformed in order to ensure that there is a solution of the problem. And then we represent here the solution of the physical system or the state problem. So the whole algorithm can be shown on the slide. So we start with the initial density. We filter the density to a filter PD. This could be any convolution here. Then we solve a state PD here using the diffusion equation. And as you see, the diffusion coefficient depends on our density distribution. Then we evaluate all quantities of interest. So this would be the objective, the constraints. And we solve a set of adjoint equations. Using the adjoints, we can evaluate gradients of our objective and constraints, and we can apply chain rule because we have a transformation of the density here in the filtering process. And we can obtain the gradients with respect to the original density discretization. And then we update the density using popular algorithm. This would be optimality criteria. MMA is perhaps the most popular algorithm for two-project optimization. We can use IPOP, HIOP in MFM, recipe-based algorithms. And we can repeat this process until convergence is satisfied and we're happy with the design. Now, where FM comes into the game, well, FM can be used for solving any of these PDEs, which you saw on the previous slide. And we can represent our density by using grid functions. We represent the state solution using grid functions. The scalable PDE discretizations allow us to scale to solve and optimize very large problems. Here we employ the bilinear, linear, or the nonlinear forms for the DFE discretization. FM provides us also with a scalable algebraic solvers to solve the linear systems associated with all this every of the PD solves, as well as in the optimization process. And of course, in order to solve them, we need scalable preconditioners, and these also coming from FM or from external libraries like Hybrid and Basic. Now, the interpolation between void and solid can be performed by using the coefficients in FM, and this provides us with a very powerful abstractions for doing all different types of interpolations without much modifications of the code. So all these features are packed in the FM library and can be used directly in the optimization process. And that's exemplified in a new example, which is being accepted in the FM repo, I think recently, a few months ago. That's an example for topology optimization. It's a kind of new algorithm, so it resembles the optimality criteria for those familiar with the LC algorithm. However, what is important to note here is the total number of iterations required for reaching the final design. Well, you can see here we need only 29 optimization iterations. Typically for LC, it would be about hundreds, sometimes 150, and it's the same for the method-harmonic asymptotes for the MMA algorithm. The example is using simple interpolation, so nothing fancy. You can easily replace with ramp or any of your favorites over there. Solving an isotropic linear elastic problem. And the design update is a kind of a new algorithm, entropic mirror descent algorithm, which is described in this draft by Brendan Keith and Thomas Silovitz, and can be found in the archives as well as the references at the end of the presentation. Topology optimization can be applied and should be applied if you want to account for all uncertainties in the real world. And to model these uncertainties, we have again the tools already plugged into FM. Those of you who remember the presentation from the last year from Tobias Burswald, it was about simulating random fields in FM. And we can apply this in accounting for uncertain walls or uncertainties in geometry or manufacturing uncertainties in the topology optimization process. And that's an example of formulation which accounts for uncertainties. So we minimize the mean value of a response of a diffusion system. It's again a similar formulation of the standard deterministic FM formulation which you saw earlier. The only difference is that we need to sample, or we need to account for the uncertainties. So therefore, evaluating the objective here requires the solutions of hundreds and thousands of PDs. Now, this is already published, so you can go on the paper and read about all the details. So that's an example of how we optimize for heat sink. So that's a standard deterministic optimization problem. So our design domain is a unit square with a boundary condition on the top. So that's the distribution of the material if we have a uniform heat influx to the computational domain. Now, if we apply random excitation, and here we can see random inputs generated by the stochastic PDE solver in FM or mini-app in FM, we'll end up with a design which is kind of forming closed loops. Now, if we look on the deterministic one, so the optimization is trying to transfer the heat as fast as possible to the support of the domain. However, in the random case, we have negative and positive influx in closed parts of the domain. So the optimization will try to locally balance the heat, and only the excess heat will be transferred to the support here. So to resolve all these malfeatures, we need to refine the mesh, and FM provides us with all these features on the fly. We can use AMR, we can just uniformly refine the mesh if we, since we don't know in the beginning where the features would appear. And of course, we can apply to other types of problems. So that's a design of a bridge, so with a random load applied on the deck. And that's a design which we get. This is the paper on the preparation, so hopefully soon you will read the full details about it. However, being able to model these fast oscillatory uncertainties in the excitation or in the geometry allows us actually to approach real problems. Until now, we could have done this with Carpon-Loeff expansion, for example. However, we cannot actually account for this fast oscillatory uncertain excitation or model fast oscillatory random processes. And here is a future example of the heatsink design with a very fast oscillatory random excitation as well. Now, this is about topology optimization. Quite often we would like to do shape optimization. And to do shape optimization, more or less the output is the same. The only difference comes into the discretization. For shape optimization, we have two choices: to represent the shape explicitly or to represent the shape implicitly. Oh, I don't have much time. I need to speed up. So what I'll talk here is about implicit shape representation. And to do this, we need to do exact integration on the level set functions, which are representing our shape. And this is already added. So there is exact body-fitted shape integration by using the external library, Alwin in NFM. And currently we are working on a native NFM implementation, which hopefully in the next 1 or 2 months will be pushed into the repo. Now, with exact body-fitted integration, we can integrate up to the machine precision. So you can see here, for example, how does it behave. We can, of course, blast the cut cells or the cut finite elements with a lot of Gaussian points. However, it doesn't matter what we do. It will flatten and we have quite huge numerical errors. However, with the exact body-fitted integration, we can actually reach the machine's precision. So one would say, why would we do this? We can project actually our topology optimization results. Well, the issue with topology optimization is that we are using H1 field, or continuous field, for approximating color density. And it doesn't matter how much we project, we will never escape from the gray regions in the topology optimization process. However, with shape optimization, we can actually take our topology optimization results, we can shape optimize them, and we can account for exact stress concentrations, for example, or temperatures and so on, what we're interested in the process. Now, something which is also coming as an example in NFM is for shape optimization is CutFEM discretizations. It is tempting to, for CutFEM, those of you who are familiar with the problem, that we need to stabilize the cut cells. It is tempting to use standard stabilization, which is used in topology optimization, where we use weak material in the cut cells. However, I should warn here that actually this is not consistent. And so we have to be very careful what will be the value of this stabilization. We can use consistent stabilization and we can use, get high order convergence for our solvers. And finally, okay, I still have 5 minutes. I would like to stop on optimization approaches with NFM. Now, for large structures, like the one on the slides, we can fully resolve the structure, perhaps, and solve for a single density distribution or single excitation. However, in topology optimization, we do need to do this process hundreds of times and sometimes thousands of times. and it's very expensive. So, for example, solving this problem here would take approximately 4 or 5 hours on 1,000 calls. And we cannot afford doing this for topology optimization. So therefore, what we can do, we can take a unit cell from our computational domain and create a reduced order model. And in this case, we're using machine learning for creating a relation between an average velocity in these unit cells and the gradient of pressure. So we can get a representative unit cell and we can blast it with different acceleration terms. So we can find this relation. This does not come for free. It costs quite a lot since we have to simulate this unit cell for many different directions. However, once we obtain this, we can actually do the optimization. And here is a comparison between reduced order models simulations and full result simulation. We can do this in 3D, just in 2D is one can see the differences. And here is a cut between on the velocity distribution for two different sections. And we can see that with reduced order models, we cannot resolve the high oscillatory behavior of the flow. However, we can resolve quite nice the average behavior. And for the average behavior, the average is 2.3%. And now we can employ this, of course, for optimization. So we can vary the thickness of the properties in the cell, or we can vary the different geometries in the cell. And here we can see a distribution obtained by using the reduced order models, using visualization. One would say, wow, it's very simple, it's quite boring, but actually it's quite intuitive design. So what's happening here is that we have one main channel forming for ensuring that the pressure drop is not too big, so we can pump the fluid through the system. And at the same time, the optimization is trying to accelerate the flow in these regions and extract as much heat as possible from the bottom of our domain. With this, I will conclude the presentation. Now, the new features coming in MFM, which would aid topology and shape optimization. So we are actively working on automatic differentiation. Currently, we have native MFM implementation of forward mode. One can use external algorithms like Codipact for reversing forward mode. And we are actively working on using enzyme for reversing forward differentiation in MFM. Now we have a PR, we're preparing a PR of native method of moving asymptotes optimizer in MFM, which hopefully would be GPU ready at the end of the next year. We would soon push PR on a native MFM integration for immerse discretizations. And we are working on immerse solvers and the joints for linear, nonlinear elasticity, diffusion, advection, diffusion, and stuff. Thank you very much. And any questions are welcome.
Thanks very much, Bojan, thanks for the great talk, and thanks to all the speakers in this session. See, we can probably take one or two questions. I also did notice in the Slack there were some questions. So maybe Joe, do you want to unmute and ask your question?
Sure. I guess it's a loaded question. Number one, I guess, when is this last slide? When is the time frame for this last slide? And I guess when it comes to these immersed boundary type cut cell methods, which one are you having the most success with? Because there's a few that I see. There's some already in MFM. There's some in PRs. Then there's techniques that aren't in MFM yet. So I guess I'm kind of wondering where your thoughts are.
So what you see on this slide, the timeline is by the end of this fiscal year. So September 24, we should have these features in MFM. For the immersed front-end and discretization, I'm currently implementing an example with CutFEM, standard CutFEM discretization by Burman and the Swedish teams over there. I mean, we have an example also in MFM using shifted boundary techniques.
Yes, I saw that. And then I see the new one. I pasted the pull request in there as well. There's the other one that uses the highly accurate integration scheme on implicit surfaces.
Sorry, this one I don't know.
The 2013 paper, I forget who it's by, highly accurate surface integration on implicit surfaces. There's a pull request in MFM for that.
Okay, I need to look at it. I haven't seen it. Is that yours? Or which one?
Is this the Alchemy work?
No, we have another pull request for.
It's from
JP. Yeah, for JP. From JP.
From JP, yes.
Yeah, so this one is coming as well. So these are just two alternatives for integration on implicit geometries.
Yeah. Thank you.